Hello and welcome to Tonight at 8 from the RSGB. The advent of digital modes has enabled radio amateurs to receive and decode extremely weak signals which would otherwise hardly be possible using conventional analogue radio. Our guest this evening is Gwyn Griffiths, G3ZIL, who's built his own equipment and used some of these modes and tools as part of deeper research into radio propagation. Welcome to Tonight at 8, Gwyn. Could you give us a brief overview of what you'll be covering this evening?
Thank you, David. It's my great pleasure to give this RSGB Tonight at 8 talk on what we can learn about propagation from the reception reports of digital modes. In particular, I'll show how data from WSPR and its less well-known stablemate, FST4W, can tell us whether propagation was via one hop, two hops, a chordal hop, or by a mode that was quite a mystery to me. So there'll be a bit of a detective story tonight.
Oh, this sounds fascinating, and we're looking forward to it, Gwyn. And if you're watching this on Monday, the 5th of February, then this is live. And you can ask questions and make comments on either YouTube chat or BATC messaging at any time during the presentation or straight afterwards. Please include your first name and call sign if you have one within every message. And note that you can make this video stream fill your screen on most devices, usually by double-clicking on the picture or pressing the full screen button. But now, back to Gwyn to find out how digital modes can help our understanding of propagation.
Thank you, David. Now, I mentioned one hop, two hop, chordal hop, and a mystery mode in my introduction there. Well, here are some graphics that I'll be drawing upon during this talk. These graphics are ray traces from the transmitter to the landing points of particular rays setting off at different angles from the transmitter and arriving at a receiver at a certain distance away. And this graphic from PyLab, a simulation program, shows one hop. Here we have greater distances out to 5,000 kilometers by one hop, two hops. And here we have an example of a chordal hop. So this low angle ray has emanated from the transmitter up to the ionosphere. It doesn't hit ground again. It goes to another hop in the ionosphere over here and comes down to the ground at about 7,000 kilometers. So that's a one hop, chordal hop mode. And then we have a mystery mode. This is going to be the detective part of the talk. A mode that didn't fit in with what I learned from textbooks. So what on earth was going on? So here's an outline of my talk this evening. After a few words on my amateur radio and technical background, I'll show some early efforts with hardware for WSPR. One thing that intrigued me was that WSPR spots could suddenly disappear. And there were times with hardly any WSPR decodes at all. I wondered why. And I was keen to know more about how signals actually got from here to there. For example, in this graph, from Southampton, where I live, G3ZIL, to Stuttgart. Propagation shouldn't be possible at this time of day on 14 megahertz, and yet it was. So what on earth was going on? So this talk is the story of how I've relearned and seen for myself HF propagation basics, as in, say, the RSGB handbook. But I was unable to explain propagation on several parts from descriptions in the handbook. The explanation, when it came, was a real surprise. And along the way, I learned valuable lessons in just how useful digital modes can be for propagation studies. As a teenager, I was proud of being an associate member of the RSGB, A6143, as in this QSL card. And like many of my generation, Pat Hawker's technical topics articles in radio communication were an important and indeed memorable part of my technical education. And I'm still nostalgic enough that equipment from those years forms part of the yesteryear corner of my shack, in particular the World War II PCR receiver. That was my first one as an SWL. And then the first setup as GW3ZIL on Anglesey, a Star SR550 double conversion receiver, and the venerable KW Viceroy transmitter. They're still there and have been joined with other equipment of that era over the years. My professional career was in the engineering and applied physics side of oceanography. So it had little to do with radio, but there were parallels. For 2 decades, I worked on sonar systems to study biology and physics beneath the sea surface. This is a graphic from the Strait of Gibraltar. On the y-axis, we have depth from the surface at the top down to 300 meters. And on the y-axis is time, covering 75 minutes. And the color scale shows the strength of acoustic echoes at 38 kilohertz. Now that has a wavelength of 4 centimeters at the speed of sound, 1500 meters per second. And what's shown is a series of internal waves riding the interface between Atlantic water near the surface and Mediterranean water beneath. And I've drawn on my professional experience of probing the ocean with sound to probing the ionosphere with radio waves, now purely as an amateur or citizen scientist. And on retirement, I did return to amateur radio. And after a little while, I became interested in WSPR, the Weak Signal Propagation Reporter, as it offered a mix of hands-on design and construction and the challenge of understanding what reception reports were telling me about HF propagation. My little palm-sized direct conversion receiver, shown on the right here, worked very well. The trickiest part was adjusting 3 trimmer capacitors at the front-end crystal filter to position the passband at the WSPR band and the notch at the lower sideband image frequency. And here's a practical wireless article that I wrote back in April 2016 on this form of receiver. Now, I was lucky enough to maintain contact with many of my researcher colleagues, and in particular from the British Antarctic Survey. And somehow I persuaded an old colleague, Jeremy Wilkinson, to take that WSPR receiver, the palm-sized one, onto this Korean research icebreaker, the Araon, on a cruise that he was joining in the Arctic. So he flew out to Alaska, joined the ship there, and most of the work was up in the Chukchi and Beaufort Seas here, about 82 degrees north. And he took the 10 megahertz version of my WSPR receiver, and over a period of 8 days, so 11th to the 20th of August 2016, the receiver made 3 decodes. Yep, 3 decodes in 8 days. So Jeremy was not a radio specialist, and none of these decodes were from North America. They were from this the Asian side. So what on earth was going on? Were there hardware problems with my receiver? Had the crystal oscillator shifted? Had the trimmers on that crystal filter moved? Was the Raspberry Pi keeping time over the network? Was the antenna actually connected? Was the propagation really that bad to the Arctic? Now, this experiment came up with all those questions and more. So how on earth do we try and answer them? I knew somebody that would be able to help. I'd made 4 voyages to the polar regions on the Royal Research Ship James Clark Ross, and knew Mike, GM0 HCQ by reputation. And through this collaboration, we would be able to use the Sailor HF receiver on the James Clark Ross on 30 meters with WSJT-X on a PC decoding WSPR. And I'd have it running from Southampton to the Arctic and back. So this gave us a good starting point. And as I live in Southampton, I'd be able to compare the number of decodes from the ship at the start and end of the voyage with my own. And Mike would be able to keep his professional eye on the equipment. The map on the right shows the track of the ship from Southampton through the Dover Straits, up the North Sea, off the coast of Norway, up to Svalbard, and then up to about 82 degrees north, well into the Arctic Ocean. And black spots show the locations of European whisper transmitters. And this circle here is the typical skip zone from Southampton that I'd not expect to decode. And these arcs here in cyan and red show the auroral region. Now I'm going to show a number of graphs tonight. The one on the left shows the spots received. Y-axis on a log scale here is the distance in kilometers from the transmitter to the ship, wherever the ship was on its track. The x-axis is the day of the year, Julian day. Now day 180 at the start here is the 29th of June, and day 230 is the 18th of August. So this is midsummer. As the ship left Southampton and travelled north, more spots were received. Now in this, as in other plots, I'll be showing contours. So the greater the contours, the more towards red, the greater number of dots there are in this region. So here we are in Southampton. As we sailed up the North Sea, there were more and more dots because we were travelling now where we could pick up those transmitters that were in the skip zone when at Southampton. But as the ship continued north, we received fewer and fewer spots. So here we are, here point at 76 degrees north. At Glitchmail, no data around day 198 here, but as is crystal clear, very few spots were received with the ship at its furthest north, 82. So here we have a professional ship's receiver, a professional radio operator, and still there were very few whisper spots received. So maybe my receiver on the Aran wasn't that bad at all. So here was evidence that the poor outcome can't have been entirely down to deficiencies in the hardware. Propagation effects must be at play. Now this is a graph from Dr. Steve Franke, the F in FT8, which deserves to be better known. It shows that it isn't just the signal-to-noise ratio, here on the x-axis, that is important to the probability of being able to decode a whisper spot. Doppler frequency spread is also important. Doppler spread is a broadening of the signal spectrum that takes place in the ionosphere due to movements, velocity gradients, and turbulent motions. There is also frequency spread due to jitter or phase noise in oscillators within our transmitters and receivers. It all adds up, and hence I'll use the more general term frequency spread in this talk. Now, users of whisper often talk about a threshold of about minus 30 dB for a decode. So here we have minus 30 dB. But we see that it requires a frequency spread of less than 1 Hertz. You've got to be to the left of this line here, which is 1 Hertz frequency spread, for that minus 30 dB threshold to be achieved. And as the spread increases here to 2 Hertz and then 2.5 Hertz, one needs an increasingly greater SNR to decode. Being a very narrow band mode makes whisper more susceptible to frequency spread than wider modes such as FT8. Now, to avoid confusion with later notes, I've said that the spread values on this graph are between minus 10 dB points on the signal spectrum. All values I'll show later are between minus 3 dB points, hence they're smaller. They're about 40% of the values shown on Dr. Franke's graph. So our limit will actually be more like 1 Hertz than 2.5 Hertz for Doppler spread. So I now know that Doppler spread is important, frequency spread is important. Now, how on earth could I measure the frequency spread of whisper spots as well as the SNR. Well, I couldn't, but in WSJT-X version 2.3, two new modes were added, amongst others, FST4 and FST4W. The FST4W being a whisper-like beacon mode designed particularly for LF and MF, but they came with the ability to measure frequency spread if you turned on an option in rather a curious way by putting an empty file called plotspec in the startup directory. However, we now have a new variable, but how do we log the frequency spread? There were other hurdles. There were no documented use or users at HF. And we won't want equipment's frequency spread, the oscillator jitter or phase noise, to be contaminating our results. And there's also no compensation for drift in FST4W. So that again pushes up the technical requirements on the equipment used. Now, the first hurdle was actually quite easy. Since 2020, I'd made some small contributions to a substantial project of Rob Robinett, AI6VM, Whisper Daemon. Now, Whisper Daemon is a decoding and reporting system for Whisper and FST4W that is more robust, extensible, and capable than that at whispernet.org and within WSJT-X. And so it was very easy for us to add frequency spread measurements into its database. But what of the other hurdles? As for no users hurdle, I've been lucky enough for several years to collaborate with an informal group of amateurs in the USA using Whisper Daemon. And they were willing and able to use FST4W and report frequency spread. And as for the equipment-induced frequency spread hurdle, most of these collaborators were using Kiwi SDRs, software-defined receivers, which, as standard, come with GPS-aided master oscillators. The oscillator is not phase-locked or even frequency-locked, but at least it's a decent starting point. The experiment needed one station to be within line of sight of the transmitter, and that station, WW6D, did not have a Kiwi SDR, but an LAD FM duo with an external oven-controlled crystal oscillator. His logging, Doug's logging, was by standard WSJT-X. And after adding the empty plot spec file, the frequency spread values appeared on the right here in his console, and Doug kindly copied those down manually to send them to me. So his contribution to this experiment was quite key. And I'm grateful to Lynn, WB7ABP, Santa Rosa, Sonoma County, Northern California, just north of San Francisco, for providing transmissions of FST4W-120, and that signifies it's the 2-minute long variant, the same length as Whisper. His Apache Labs Anon SDR transceiver had a GPS-disciplined master oscillator, and this assured very low jitter and phase noise, and essentially no drift for our transmitter. So to summarize, I was anticipating to see frequency spread as on the middle graph on the line of sight path. That is frequency spread of 0.008 Hertz. And I'm going to be referring a lot this talk to millihertz. So that's going to be 8 millihertz. What I'd not want to see is what's in the bottom graph here, where x-axis is frequency in hertz. And if you have a whisper transmitter, which would be absolutely fine if it drifted 0.1 hertz over 2 minutes, that would imply a spread of 110 millihertz, which would not suit these measurements at all. So you can see the sort of quality level on receiver and transmit oscillators that we were after. Now, the purpose of the first experiment in December 2022 on 14 megahertz was to gather frequency spread and SNR data over enough paths of different lengths to be sure of seeing instances of surface wave, right here, so exaggerated, one hop propagation, as in this area here, so in this example out to 1,000 kilometers, examples of two hop propagation out to 1,000 and then out again here to 2,000 and beyond. I'd not expect to see near vertical incidence skywave on 14 megahertz, as the F2 critical layer frequency, F2 layer critical frequency was unlikely to be high enough. But I would expect to see instances of no propagation. That is, when a receiver was in the skip zone from the transmitter. That is, when the receiver was closer to the transmitter than the landing spots of one-hop paths. So here is a map showing the locations of the transmitter of LIN WB7ABP in red and the receivers in yellow. And this spread of receivers gives us what we were after, from surface wave, one hop, two hop, and so on. And we'd gathered data mostly on mid-latitude paths, mostly around 40 degrees north, but also on a path up to the Arctic Circle. Remember my interest in the dropouts in propagation up to the high Arctic. And we could compare and contrast measurements on the over-water path out to Maui to the over-the-land path of similar length to Long Island. Now, time doesn't allow for all of the results to be described tonight, but I hope that the main findings from these paths will become clear. For each path, I'll show a pair of graphs. Both are time series. Time will be in UTC on the x-axis. And the top graph here shows signal-to-noise ratio, SNR. As is usual with WSPR, it's defined in a 2.5 kilohertz bandwidth. And the bottom graph shows frequency spread in millihertz. And let me repeat yet again, millihertz. And these are the results for the 2.4 kilometer path from Lynn to Doug WW60 on almost line of sight suburban path. And this shows that with this set of equipment, a GPS disciplined oscillator in the transmitter and an oven-controlled crystal oscillator in the receiver, it did not add any measurable spread to that intrinsic to the 120-second length variant of FST4W, here of the order of 5 to 10 millihertz. I got the same spread actually at baseband when I connected the audio from one computer running WSJT-X to another one as receiver. So we should be able to decode down to minus 32 dB SNR for these forms of very low spread surface wave signals. So we understand surface wave, we think, for frequency spread. Now I increase the path to 40 kilometers. Recall that we're using 14 megahertz. And my expectation was for a weak surface wave signal with very low frequency spread, as it hadn't been anywhere near the ionosphere. But the results shown here were not at all that simple. So let's look at the signal-to-noise time series, the upper graph first. And what I've done is to add curves in cyan for the sun's altitude, and these help you pick out daytime. So the middle of the day is the peak of these sun altitude curves. Now the two nights, A1 and A2, show some variation in SNR, and the levels were different on the 2 days. But daytime SNR here, where I've labelled B, was more variable. Far more variability here during the day in SNR than during the night. Now, on this information, you might shrug your shoulders and say, well, no one expects SNR to stay constant. But look at our new measurement, frequency spread. During the nighttime, A1 and A2 are much the same. But there's a dramatic increase in frequency spread during the day. Why? Let's have another look at a different form of presenting this same data. And this is a scatter plot. So on the y-axis, we have the frequency spread in millihertz from 0 to 1000 millihertz. And on the x-axis, we have signal to noise ratio. And the contours, as before, help pick out distinct clusters. So clusters A1 and A2 are separate in SNR, as we've seen for the 2 days, but they both have the same median frequency spread of 59 millihertz. Cluster B here is quite different. Its median frequency spread is over 10 times greater at 624 millihertz. And what's clear is that there is no real middle ground. These are 2 different propagation modes. Now, A1 and A2 are undoubtedly surface waves, as I'd expected, but I had no idea whatsoever about mode B. We also see a technical point that a GPS-aided QESDR adds more frequency spread than we'd like, suggesting that we really should use GPS-disciplined oscillators for future experiments. Now here we've increased the range to 960 kilometers, so propagation must be via the ionosphere. In the time series, we have the sun altitude curves again, so we can identify day and night. And I've labeled 3 intervals, I for ionosphere, so I1 during the day, which had to be 1 hop, and its frequency spread was reasonably low, at about a median of 87 millihertz. The receiver was a GPS-aided QESDR, and as we'd seen a median spread of 59 millihertz on a surface wave path, I definitely got the impression that the actual frequency spread on a mid-latitude 1-hop path was likely to be lower than we were able to measure with a GPS-aided QESDR. Now, mode I2 is still a mystery to me. It has decent SNR and a low spread. It's possibly sporadic E, not unknown in midwinter here at the very end of December. Now, mode I3 is quite different. It had a low, yet pretty consistent SNR, and it had a high frequency spread. The median spread at 623 millihertz was virtually identical, spookily so, to the 624 millihertz of our mystery mode B on the 40-kilometer path. But that seemed very strange. That implied that during the day, there was a propagation mode on 14 megahertz via the ionosphere on a 40-kilometer path. Again, what's going on? Let's push the path length out to 3,762 kilometers over the Pacific to Maui, where AI6VN Rob has an unattended GPS-aided QE. During the day, we had mode I4, high SNR, but with a moderate frequency spread, a median of 266 millihertz. Now at night, mode I5 had a lower SNR and a lower frequency spread, a median of 83. Recalling that the one hop on 960 kilometer path had a median spread of 87, I was pretty sure that mode I5 was one hop. And indeed, PyLab ray tracing showed that one hop was possible that time of the day. Mode I4 was therefore likely to be two hop, and again confirmed using ray tracing. So now we're starting to build up a picture of frequency spread. One hop as less than 100 millihertz, two hop as here about 260 millihertz. The mystery modes B and I3 showed frequency spread over twice that of two hop. Next, let's look at a 679 kilometer path, which I'd expect to be within the skip zone at 14 megahertz, if you recall the earlier ray trace that I showed, that had the first landing points around 1,000 kilometers. Now, around the middle of both days, I've labeled mode I1 on the SNR and scatter plots. Because of its high SNR and low frequency spread, so high SNR, especially on the second day, high SNR and low spread, I1, there it is in the cluster diagram, I'm pretty sure that that was one hop propagation. But far more common, happening before I1, so it happens before the critical frequency is high enough to support one hop, and after the critical frequency has dropped, we have mode I3 again, which we recognize because of its low SNR, down here, and high spread. The median spread 578 millihertz, not far off from I3 and B as we've seen before. Whatever this mode was or is, it's not rare. We've seen it on paths from 40 to 960 kilometers, at night, during the day, day in, day out. So it appears to be an ionospheric propagation mode that seems to work above the maximum usable frequency. To show that this mode does not just occur over North America, my own 14 megahertz FST4W signals from Southampton, received by my good friend Nigel, G3ZIL, Beckenham, South London, over a path of 108 kilometers during the day, had a median spread of 614 millihertz. Now there's this strong cluster. It's that mystery mode yet again. So it's not confined to the US, it's here in Europe as well. So after much reading, I began to think that the mystery mode was two hop side scatter. Let me explain. In this diagram, we have the 960 kilometer one hop path from Lynn WB7ABP to KA7OEI, the Northern Utah SDR site. That's in white. That's one hop. That's along the Great Circle. That's what we saw as I1. As evening progresses and the F2 layer critical frequency drops, the ray landing points from California move beyond KA7OEI, and the receiver falls into the skip zone of the Great Circle one-hop path. So let's say that the landing spots now start at 1,300 kilometers, well beyond KA7OEI. A one-hop path, however, of 1,300 kilometers might take the signal to the ocean of Baja California, as shown on this light blue diagram. The large majority of the signal power will be reflected from the sea surface in the forward direction, the dashed line, and continue on to receivers to be heard as the second hop. But some small fraction will have been scattered at all azimuth angles, and one ray could follow this path back up to the ionosphere, one hop, and then back down to ground at the receiver at Ka7 OEI via one hop propagation. So hence the name for this mode. We have two hops, so two hop side scatter. So let's test this idea. And I've now tested it on several paths. And tonight we're going to have a look at the path where we've seen the mystery mode to dominate. That from Lynn in California to Rick KK6PR in Oregon, the 680 kilometer path. Now, when we look at a propagation prediction output, for example, from VOACAP here, and we look at 14 megahertz, it's in the white. There's no indication of an open path at 14 megahertz, but clearly one exists. Simple ray tracing is no help, as is the handbook. We're well within the skip zone. The ray trace also shows KK6PR to be well within the skip zone. This isn't any help. But what is helpful is that the ray trace here shows a focus of landing spots at the leading edge of the zone where one hop propagation does become possible. We have both low and high rays. As you see, two rays converge on this point. And that will be important in some results we'll see later. There's an aggregation of ray landing spots near the edge of this reception zone. So ray tracing in that simple form isn't helpful. But ray tracing actually is very helpful in its three-dimensional mode. So we've introduced the idea of ray landing spots, where a ray lands from the transmitter. Think of this 3D ray tracing as conventional 2D ray traces stepped in bearing from the transmitter in 1 degree increments. First, let's do that for the transmitter at WB7 ABP. And we get the ray landing spots as black dots shown on the first map. So there's an agglomeration, so many dots here that it's almost solid black, but they're individual ray landing spots. And as we go further out in distance, the ray landing spots become further apart. And there is also a difference between to the north and to the south because of the ionospheric characteristics. Now, KK6PR at the receiver is well within the skip zone. Now, in an academic paper on two-hop side scatter, the authors placed a transmitter at each and every one of these black spots and tested to see if there was a path from that black spot to the receiver. Now, I thought that was a tedious approach and needed a great deal of computing time. So instead, I assumed that reciprocity held well enough for my illustrative purposes. And so I place a transmitter at the receiver location and calculate its landing spots in magenta. For step 3, I multiply the number of landing spots from the transmitter and from the receiver in each 1 degree by 1 degree latitude longitude box. For example, that's this tiny orange box that you can see here. And this gives me a measure, a metric of the likelihood of backscatter from that area, everything else being equal. And from this map, we can get an impression that there is much overlap, hence high values of likelihood metric to the west and to the southeast. Now, this becomes clearer in a contour plot of the likelihood metric, the highest values being the regions of most intense red. And so out here to the west is where the model suggests side scatter was happening at 0400 UTC. And the thin ring is because of the ray path geometry and from that focusing effect that we saw of the high and the low angle rays near the edge of the skip zone. But is this model result at all credible? Lynn, WB7ABP again, was kind enough to perform a rotating antenna experiment. He'd rotate his 5-element 20-meter Yagi in 10-degree steps every 4 minutes. If the path was over the Great Circle to KK6PR, the maximum signal level would be on a heading of 010 degrees, so shown by that arrow there. It wasn't. Instead, the maximum signal level heard at KK6PR was with a beam heading of 320 degrees out in this direction over the ocean. And you can see the beam pattern of the signal level with azimuth angle as the blue dots. So plotting the Yagi's beam pattern via surface wave at a distance of 2.4 kilometers gives us an estimate of the antenna's beam pattern, but we don't really know what the beam pattern actually looks like at an elevation angle at this range of about 1,500 kilometers. So our model suggested that there should be a peak at around an azimuth of 280 degrees here, where the red is most intense. But in practice, KK6PR had the maximum signal with Lynn's beam heading 320. So we have a discrepancy of 40 degrees clockwise. But I still consider that a fairly credible agreement for this quite simple experiment. The peak certainly was not along the Great Circle direction of 010. So how might the area of side scatter vary throughout the day? So we've got some sense of where it occurs at 0400 UTC. Here's an animation over 24 hours, starting at 0000 UTC, rather faint up in the top left here. So that's afternoon, 1600 UTC local time, where we saw that the peak, and I've intensified the color scale here, was out to the west. During the afternoon, the peak moves further to the west, and so in the evening, and weakens before becoming an arc to the south. In the early hours local time, we'll see a peak forming to the east, and around noon, it'll flip to and fro to the west before settling to the west in the afternoon. So here goes on the movie clip. There it goes, moves out to the west, becomes thinner, signal level goes down. Now in the morning, the peak starts to form to the east, and the highest level flips to and fro before settling in the west. So a fascinating change in the predicted area of backscatter through the 24-hour period. Now, unfortunately, I don't have a 24-hour rotating antenna experiment to show. So instead, let's look at the variation of signal level throughout the day as a scatter plot with contours, as we've seen before, and as a histogram of the spots received each hour. And on the small map, I've plotted the locations of the maximum side scatter metric for each hour. And I'll ask your indulgence in not expecting exact correspondence in time between model and actual data, concentrating more on the key features. So from about 0900 to 1400 UTC in this period, there was a drop in the number of spots decoded and a drop in the signal level. And I'd suggest that this is when we saw that very thin, whispery arc out to the west, moving to the south, and then round to the east, at the greatest round-trip distance from the transmitter to receiver, when we had lowest signal level and fewer spots. But at 1400, the signal level increased somewhat and the number of spots rose. But there was also a dip in the number of spots decoded, even though signal level was high between 2100 and 0100. And I'd suggest that this is because of excess frequency spread, with signals at the receiver arriving from both the land to the east and the ocean to the west. And we see from the map here that the location of maximum metric flipped back and forth during those times. And I think there was so much spread that we couldn't decode the signal. So we have a drop in the number of spots received per hour, even though the SNR, the signal level, was high. So leaving two-hop side scatter, let's look briefly at chordal hop, a propagation mode where there is an ionosphere to ionosphere hop that avoids a ground reflection, as here on this PILAB ray trace. Now, I come clean on the slide. I can't quite get the rays to reach ground at K6 RFT, Peter. And I tell myself that it's because the model of the ionosphere within PILAB is more of a climate than day-to-day ionospheric weather. And a chordal hop is certainly not seen every day. Greater than modeled ionosphere electron density here at the second hop would be enough to bring this ray down to ground at this range of about 6,900 kilometers. And the graph here at the bottom is frequency spread on the y-axis, 0 to 1,000 millihertz against time of day for several days. And on 2 of those days, and only in the morning, there were clusters of spots with low frequency spread. The cluster that I've ringed in blue, and on a different day, the 3rd of January, this cluster that I've ringed in orange. And those 2 clusters had a frequency spread of 100 millihertz or less. And from all I've learned today, given that low spread, less than 100 millihertz, those spots had not reflected off the ground or the ocean. And so they were quite possibly this ionosphere to ionosphere chordal hop mode that we've been able to identify because of the low frequency spread. We couldn't say that from just SNR. So having explored frequency spread on several paths, I return to where I started, the Arctic. On a path from Southampton to VY0 ERC on Ellesmere Island on 14 megahertz. The scatter plot on the left is from my path to Tom WA2TP on Long Island. So this provides a mid-latitude reference. And here we have a median spread of 296 millihertz, which from my results seems to suggest 2 hop. Now the shorter path to VY0 ERC has only a quarter of the number of spots decoded, and it has over double the frequency spread. So I am pretty sure that there were spots with frequency spread of over 800 millihertz and SNRs perhaps below -20. This area here just were not decoded, and we can't see them, so we can't plot them on the graph. So I think excess spread is far more likely to be the problem than simply lack of SNR on these Arctic paths, and that's why we have so few spots on the James Clark Ross on 10 megahertz and on the Korean research vessel, the Araon. So as I start to draw to a close, I've applied many of the techniques I've shown tonight to studying the effects on HF band propagation of the 13th of October 2023 eclipse over North America. And you can find my talk on the Norfolk Amateur Radio Club YouTube site. There were fascinating results on a 5,000 kilometer path from Costa Rica to the US West Coast. Propagation was interrupted on the second and third hop on 28 megahertz at distances of around 4,400 kilometers, and circuit reliability, top graph, was reduced at 5,000 kilometers. And those results set me thinking, for there is, on the 8th of April 2024, a total eclipse over North America following this path. Now it peters out in mid-Atlantic, it won't reach us. But the second and third hops from here, so myself at Southampton, first hop out to the mid-Atlantic, second hop here, about the longitude of Newfoundland, and the third hop over the US, in New York State, Ohio area, and for example on this path to K6RFT in Missouri. So the second and third hops of 21 megahertz up to 28 megahertz will definitely be in the zone affected by 80% occlusion of the sun during the total eclipse. And so I think it would be fascinating for UK and indeed Northern European amateurs to use WSPR on 21, 24 and 28 megahertz on the 7th to the 9th of April this year to bracket the day before, the day of the eclipse, and the day after. And so I would certainly encourage WSPR users to do that, and I look forward to working up the results. So to close, here is a summary of what I've learned over the last 18 months of studying frequency spread at HF. And please appreciate this is work in progress, may be revised and indeed expanded. Indicative equipment spreads are in magenta. I was really surprised just how low frequency spread could be via the ionosphere on one hop. And it's only through using GPS disciplined oscillators, both ends, that we can properly measure such low spread. And that goes for chordal hop, ionosphere to ionosphere modes as well. A plain, simple crystal oscillator typically has a spread of 300 to 400 millihertz over 2 minutes. That's just not good enough for these studies, and shows actually that the ionosphere is surprisingly stable. Two-hop side scatter has been a complete revelation and deserves further study and appreciation. So it may seem that the information from a WSPR or an FST4W reception report is both minimal and ephemeral. But as I've shown tonight, there's a great deal we can learn about HF propagation from these measurements made carefully and systematically. Thank you.
Thank you very much, Gwyn. We've got a slide there actually, which we'll actually just, if we could just show that again, Tammy, just so that everybody at home has got a chance to have a look at that. Of course, if you've been watching this, it's quite a deep subject, and but if you're watching this now live, you'll be able to watch the recording of this available on the RSGB YouTube site, you know, within a matter of hours of this finishing. So there's some links anyway that might be useful. And of course, Gwyn, you've got your contact details at the end, because I was going to ask you, you've invited amateurs in the UK to help you on the 8th of April eclipse. So that would you like them to correspond with you over that? That again at the bottom of this slide.
I'd be delighted to do so.
Good. Okay. Well, that's excellent. I will just leave it there just for a moment more. So anyway, if you've any questions or comments for Gwyn now, and you haven't already done so, please do it now on either YouTube chat or BATC messaging. And please don't forget to include your first name and your call sign if you have one as well. There we are. Thank you. So, Gwyn, you said, I think in your summary at last moments, you said this has been so interesting for propagation. We should say that you're an associate member of the RSGB Propagation Studies Committee. So how do you think the information that you've gained so far will affect and can affect our understanding of propagation more?
I think it's this mode, the side scatter, that's really surprised me. I mean, it's there in academic journals, and there was quite a few investigations in the 1960s done about it. But often, as radio amateurs, we may have, if you like, the folklore that there are times when you will hear stations within a few hundred kilometers on the higher HF bands. But being able to put a name to it, being able to understand, and certainly for me, it was the self-training part of amateur radio, the rediscovery for oneself of exactly how our signals do get from A to B. The fact that when a signal fades away, suddenly drops in level, it isn't just that it's getting weaker. The propagation mechanism is changing drastically. And it's trying to then push that deeper to say, can we actually devise experiments like I did in that rotating antenna one, that then tries to tie up these computer tools that we have to model the ionosphere, like the ray tracing, with actual measurements. Because I think the amateur radio community is terrific now in its ability to make measurements that can then challenge the models that arise out of professional ionospheric physicists.
Yeah, and I guess if you can, my understanding anyway at least, is that if you can improve the modelling, then you can also improve the forecasting as well.
Indeed, as I showed there, that VOACAP display just had white for 14 megahertz. So some of those propagation models that amateur radio community uses day in, day out do not represent well these modes such as two-hop side scatter.
Okay, yes, thanks. Well, we've got a question now from Steve M1STH. He says, firstly, a fascinating talk. Could this lead to better models for propagation beyond digital modes you covered in today's presentation?
Indeed. And you'd start to get a handle on it, if you like, from how many dB down is the side scatter compared to the main mode. So maybe 20 to 30 dB down. So of the order of 4 or perhaps 5 S points. So if there is an S9 signal there, it might go down to S4, but that might still be workable in certain situations. So it certainly isn't just a weak signal or digital mode effect. I think certainly for CW and sideband, they would be able to make use of these modes and perhaps in a better understanding. And in particular, those few situations perhaps where on the HF bands, receiver and transmitter are both using directive antennas, Yagis. And they would have, for example, for a schedule, and they will use the great circle path. Well, as we saw in that experiment, if it's during a time of side scatter, that's not optimum. You'd want to divert and point your antennas towards what would be the common backscattering or side scattering region, which that model that I showed of 24 hours varies through the day. So you'd point your antennas well away from each other. Now that might be a bit of a strange thing for an amateur to do.
It certainly would look rather strange, wouldn't it? I presume that without these digital modes, you couldn't have done them, even if you had the ability to receive the weak signals, because am I right in thinking that the digital signals allow you that precision that you talked about? It's so important to be able to measure these very subtle changes.
You're right. And, I must pay tremendous tribute to the WSJT-X development team for the signal processing that goes on for them to give you a value of SNR and to give you a value of the frequency. Now that's all done for me. And it's the multitude of data as well. We can get reception reports every 2 to 4 minutes, for instance. So we can start to build confidence in our measurements. And that you saw from my use of the contour diagrams that we have many spots in there and contours, and they form clusters. If you only had a few measurements, you might not really get that picture that there really is a very tight relationship for each of these modes. They have a fingerprint in spread and SNR, and the fingerprints are distinct between different propagation modes. And it just gives you hundreds of data spots per day.
To give you the resolution of data that you need to make sure, I guess, the experiment is valid.
Absolutely, yes.
So finally, I think I'd like to ask you, as someone who's essentially a scientist and looked at this from in a research point of view, even though the results, I guess, were significantly and unknown, are they what you expected, or are you surprised by what you learned?
I mean, I am a radio amateur, maybe even, well, you might push it to a citizen scientist, but very much an amateur. But some of these results have surprised ionospheric physicists that are part of the Ham-Sci consortium. And there are links to that on my Find Out More page. And indeed, I'll be hopefully giving a poster in person at the Ham-Sci workshop at the Case Western Reserve University in Cleveland, Ohio, next month. So there is definitely interest from professional ionospheric physicists and people working on models in this use of the digital signals analysis to help them improve their models to become more like a weather forecast for the ionosphere rather than just climate for a month.
Well, we hope that goes well next month, and of course the eclipse that's happening in April, where amateurs in the UK can get involved between the 7th and 9th of April on 21, 24 and 28 megs, as well as VLF. So, and we did show your details there. We'll also put your contact details, with your permission, on the RSGB website after this presentation for the recording, so that people can get in touch with you. Gwyn, thank you very much indeed for tonight's interesting presentation, and thanks for all the work you and your colleagues all do, of course, on propagation, because it does enable us to have a degree of forecasting so we can know what aerials to put up, what contacts and conditions that we're likely to have. We really are grateful for all the work you do. Thank you very much.
Thank you, David, and also thanks to Tammy behind the scenes there with you.
Thank you. Yes, she's just sitting here pressing all the buttons and everything. Thanks very much, Gwyn.
Yeah.
And that concludes this webinar, and thanks once again to Gwyn Griffiths, G3ZIL, and also thanks to the team who helped put this series together behind the scenes, and indeed Tammy here as well. In next month's Tonight at 8 webinar, we have a presentation about the challenges and fun of VHF National Field Day through the eyes of Lothian's Radio Society. Well, the RSGB annual construction competition closing date of March the 1st is fast approaching, but it's not too late to enter. It's open to all RSGB members and is judged online, so you don't even need to send your projects away. For full details, visit rsgb.org/construction-competition or see the latest RADCOM. And if you'd like to see details of future webinars or watch recordings of previous programs in the series, please visit rsgb.org/webinars, where you can also send us comments and feedback. And if you subscribe to RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. Until next time, this is David G7URP signing off and clear. Bye-bye.